Okay, so we start unit 3. And unit 3 is where we start building the basis of what we need for trigonometry. And in trig, we have to have some basic geometry. And in basic geometry, everything comes, just like it did in arithmetic, from the most simple of objects. That thing right there. It's called a point. Point has 0 dimensions. Because if you're on a point, you can't move in any direction. 0 possible movement. Now, if I take that point and I drag it in a single direction, I create what is often referred to as a line. Technically, it is a line segment. Mathematical definition of a line is it goes on forever in both directions. Not horribly practical because, well, everything has to start somewhere. And we can imagine it starting somewhere and going on forever in one direction. But going on forever in both directions is a little harder to understand. The length of that line segment in geometry, distance and length are equal, they're the same thing. Length is the distance you would move to go from one end of the object to the other. This is now one-dimensional. Because if I were on that line, I could move in one direction. I always say, well, I can move right or I can move left. Isn't that 2 directions? No, it's not. It's the positive and negative of the same direction. Now, last semester, we talked about taking that line segment and moving it. Take that whole segment and we drag it down, like a stick being dragged across the sand, and it creates a rectangle. Rectangle, of course, is now 2-dimensional. It's been created by movement in 2 different directions. And of course, it has an area. And the area related to the original length of that original line segment times the distance moved again. That distance moved is often called that width. Well, today we want to look at a little bit different movement of that point. We're going to take that point and we're going to move it in a single direction. We're just going to keep going with it. That structure is called array. There are 2 properties of array. One is the starting point. That's just that point there that we started at. And the second is the direction. We measure direction kind of like a navigational directioning system. But our coordinate system, origin at that starting point of our array, east direction, 0 degrees, and we go around counterclockwise. So north direction would be 90 degrees, 180 degrees, 270 degrees, and then 360 degrees would be back at 0 again. Now remember, 360 degrees is one complete rotation. So looking at this, now I'm just throwing a number on that. That direction might be like 26 degrees. So that would define that vector there. It starts at this point and it goes in the direction of 26 degrees. I keep that same vector at 26 degrees. Now I'm going to create a second vector from that same starting point going in a different direction. When I have that second vector, there's two things about that second vector that second ray, I should say. Far enough along to call them vectors. Second ray has the same starting point, different direction. These two rays come together to make an angle. Let's put a direction on that first ray here, or that second ray. Let's say that is at 61 degrees. Angle formed here. Of course, between those two rays. Size is just the difference in direction. This angle right here, 35 degrees, because that's 26. Difference in the direction between those rays. Now, this is the classical way of defining the size of an angle. It is literally the difference in the direction between the rays that form the two sides of that angle. We have navigation used to be a pretty commonly known thing. Pretty much everybody that was educated understood how to do navigation. But you have to remember, this came from a time where only the really rich people were educated. Everybody else grew up, you learned what you could from your parents, worked beside your parents to learn a trade of some sort, and that was your life. The public schools were not really a thing yet at that point. Well, as public education became a thing, everybody became educated. So education and certain knowledge were no longer linked together. So navigation was not part of the standard education. Because not everybody was going to own their own ship and go sailing around. So they came up with this alternative way of defining the size of an angle. It's based off of the fact that if we start facing in a single direction, and if we spin all the way around, how far have we turned? 360 degrees. That is one full turn. I start facing that same direction, but now I turn around so that I'm facing the opposite direction. How far have I turned? 180 degrees. That is a half turn. That works out because 1/2 times 360 is 8. I start out facing in a direction and I turn so I'm facing directly to my left. How far have I turned? Degrees. And that is a quarter of a turn. Math there works out because 1/4 times 360, 90. So when we look at an angle, if I tell you that this angle is 60 degrees, what that means is it is 60 3/60ths of a full turn. So they've redefined that idea of degrees in the measurement of an angle to be a fraction of a full turn. Now there are some special relationships that we want to talk about. Talk about angles that add up to straight line. If I know that this smaller angle over here, 78 degrees, what is this larger angle? Well, straight line is how many degrees?
180.
180. So 180 minus 78 is, those two angles add up 180 degrees. That is called supplementary. If I have a square corner or a right angle, I have another ray coming off of that square corner. If I know that this is 71 degrees, what's this angle down here have to be? If I know the two of them, the right angle is 90 degrees, I subtract 71, I'm left with 19. Those angles add up 90 degrees, called complementary. Now, if you're anything like me, when I first learned those two words, I could remember the words, but I struggled a little bit to remember which one was which. The way I remember it is complements when you are right. Complementary goes with the right angle. But we have two angles that intersect like this, and I tell you that this angle right here is, let's call it 42 degrees. What do I know about this angle here in blue? Perfect. It's 180 minus 42, otherwise known as 138 degrees. And we know that because this is a line across here. Those two angles add up to a line, so they have to add up to 180 degrees. They have to be supplementary. Now, what's this angle over here have to be? 42. Good. That would just be the 180 minus the 138 again, give us 42. Because this is a straight line. Those two angles add up to a straight line. Again, they have to be supplementary. Brings us to the relationship between those two angles. Because they are supplementary to the same angle, 138, they have to be equal. Special name given to them, they're called vertical angles. And they're called vertical angles. They're vertical because they're on opposite sides of two intersecting lines. They have to be the same. Angles are always equal. Now, when we have lines intersect, they can always intersect in special cases. This up here is called oblique. Called oblique lines because there's nothing special about them. Now, these are intersecting oblique lines, which in two dimensions, if they're oblique, they have to intersect at some point. But remember, we're in a three-dimensional world. If this is a line and this is a line, they don't intersect, but they're still oblique because they're nothing else special about them. The two special cases, of course, we have, one is perpendicular. And perpendicular lines intersect at a right angle. Well, if we know that this is a right angle, this is 90 degrees, what do we know about this angle over here? It also has to be 90 degrees because that's a line. Those two have to be supplements. Well, the only thing supplementary to 90 is 90. They add up to 180. Now that we have that, of course, we know that this angle has to be 90 because it's vertical with that 90, and this angle has to be 90 because it's vertical with that 90. So when two angles intersect, if one angle is 90 degrees, or a right angle, all four of the angles formed have to be right angles. That's the definition of perpendicular. Intersects to form four right angles. In 2 dimensions, perpendicular doesn't have a huge meaning. We could just say two lines intersect at a right angle and it would mean the same thing. But in 3 dimensions, if this is a plane or a flat surface, and I have a line that's perpendicular to it, that means it's a right angle in every direction going around that line. So perpendicular in 3 dimensions has a lot more meaning because it's more strict than just right angles. It's a right angle in every possible direction. Parallel. Often define parallel as two lines that never intersect. 2 dimensions, that's adequate, because if they're not parallel, they will intersect at some point. But again, in 3 dimensions, I have this line and I have this line. Do they intersect? No. But are they parallel? No. So the definition of parallel, always the same distance apart. Technical jargon is everywhere equidistant, which means no matter where you measure the distance apart, they are the same distance. Now, to measure the distance between two lines, technically what you're measuring is the distance between a point on one line and the other line. So if I pick a point on one line, measure the distance to the other line, it has to be measured at a perpendicular. So it has to be from that point to the other line at a right angle to that other line. I can pick that point, I can pick this point, pick this point. Those distances should be the same no matter what point I pick on the first line, should be the same distance to the other line. And the reverse is true. If I pick a point on the second line and I go back to the first line, that distance should be the same as going the other direction. Everywhere equidistant, always the same distance apart. Now, if I have 2 lines, now in this case, I'm going to draw 2 oblique lines. I have 2 main lines. And I have another line that cuts across them. Cuts across 2 or more lines. It is called a transversal. Trans means to go across. Now, transversal is not very interesting when it cuts across just regular lines like that. It cuts across parallel lines. And those look parallel. That's my transversal there. If I know that this angle here is 112 degrees. Of course, I know all 4 of the angles now at this intersection, don't I? What's this one up here have to be? $68 degrees. Of course, that means this one down here has to be 112 because it's vertical with that one. And this one over here has to be 8. So when 2 lines intersect, even though it forms 4 angles, there's only 2 unique angles. Measurements form. They come in pairs of equal angles. Well, if I move down here to this intersection, if I think about it, if I took this line here in blue and I slid it over, it would sit exactly on top of that line, wouldn't it? So it makes sense that this angle here is just that angle there. 112 112 degrees. Well, once we have that, we know this one is 12, and this one is. If this were a formal geometry class, we would talk about a lot of vocabulary here. We would talk about interior. I'll write this down. Interior is between the parallel lines. Exterior angles are outside of the parallel lines. Corresponding angles are on the same side. Alternate angles are on opposite side. So like these two angles would be alternate interior because they're on the inside of the parallel lines, but they're on opposite sides of the transversal. These two would be corresponding interior angles. They're interior, but they're on the same side as the transversal. These two would be alternate exterior angles because they're on opposite sides of the transversal. They're outside. These two would be corresponding exterior angles because they're outside they're exterior, they're outside the parallel lines, and they're on the same side. And then these two are just corresponding angles. Notice we didn't name interior, exterior. They're on the same side. Well, you notice all those pairs that we came up with, some of them were equal, some of them were supplements. Rather than knowing all those names, which really doesn't help, knowing the interior, by the way, most geometry textbooks do a horrible job of this. They just say, these two are corresponding angles. These two are alternate interior angles. They don't explain that interior means between, all that stuff. But anyway, really all we need to know is that when parallel lines are cut by a transversal, all the angles that are formed, if we know one of them, all the other angles are either equal or supplements. All we need to know about it. So we've talked about measuring angles going from 0 to 360 degrees. But what if we want to measure something smaller than 1 degree? One degree gets broken down into 60 minutes. The symbol for minutes, the single quote, just like a foot symbol. We have to be very careful with that. 1 minute broken down into 60 seconds. Seconds is the double quote, or like the inch symbol. So again, we have to be careful with that. Usually we'll have something like 4 degrees, 27 minutes, 38 seconds. So if you've got that degrees coming first, it's pretty obvious that's minutes and seconds. But if we have a smaller angle like 48 minutes, 22 seconds, it can be a little confusing of is that minutes and seconds or is that feet and inches? Now we wouldn't have 22 inches, so that tips you off. So the only way it would be really confusing is if we had less than 12 seconds there. We are going to calculate in minutes and seconds, with the disclaimer that in reality I have never seen any manufacturer that measured to less than 5 minutes. Because to get an angle measured down to lower than 5 minutes, first of all, to see it, to measure it, is very difficult to do. You can do it if you have a comparator, optical comparator, you can see it in. Even that is tough to do. I know there are companies that do measure down below a minute, but it's all lasers. In this area, the most precise, as far as machining that I know of, is Hutchinson Technologies down in Chippewa Falls. I know that they have a couple of things that they measure to the millionth of an inch. And they have some things that they measure down to the 5 minutes. PD stands for decimal degree. So we might have an angle like 23.4652 degrees. That is in decimal degrees. DMS stands for degrees, minutes, and seconds. I might have an angle at 42 degrees, 18 minutes, 38 seconds. Now I purposely made those different angles so you don't think they're the same angle in different notation. One of the first things we need to be able to do is to convert. So let's look at converting to degrees, minutes, and seconds from decimal degrees. This is a measurement that when we calculated and got decimal feet for an answer, this is very similar to that calculation of changing that now to feet, inches, and fraction of an inch. First thing we're going to do is we're going to remove the whole degrees. 23 degrees. Now, I guess the Woods Construction Group did a lot more with this than you guys did in last semester. But we now take that decimal to 0.4652 degrees. And I want to convert that into minutes. So I'll put 1 degree on bottom so that it cancels out. 1 degree equals 60 minutes. So the degree cancels out. I'm going to take that 0.4652. That's 27.912. Again, off of there, I just want the 27. That's 27 minutes. Take the 0.912 off of that, that's still minutes. And I'm going to multiply by 1 minute on bottom. Top. Now the minutes cancel out at 0.912 times 60, 54.7. Now, depending on what you're working with, most calculators go to a tenth of a second. So they would list it as 54.7. If you list it that way, I'm okay with it. Or if you just round it to 55, I'm okay with that as well. Like I said, I don't know of anybody that measures down to 1 second of an angle, much less a tenth of a second. We can calculate to whatever measurement we want to. Doesn't mean we can actually cut something to that size. Let's do one more. Let's convert 11.8436 degrees give you a second to get a head start on me, then we'll go over it. Let's see if you're heading in the right direction here. I realize you're not completely done yet, but I'm running a short time here a bit. So we've got 11 degrees. We're just going to take that off. That's the part in front of the decimal point. 0.8436 is what's after the decimal point. We're going to turn that into minutes. 1 degree is 60 minutes. You put the 1 degree on bottom, so it cancels out. 0.8436. 60 gives us 50.616. So we're going to keep the 50 off of that. That's going to be 50 minutes. 0.616. Put it over 1, and we're going to convert that into seconds. 1 minute is 60 seconds. 0.616 times 60 gives us 36.96. So I'm going to just round to 37 seconds. 11 degrees, 50 minutes, 37 seconds. Any questions on converting from decimal degrees to degrees minutes? Well, then the next step is to go from degrees minutes seconds convert to degrees. So here we start at the very end and we work our way backwards. It's the reverse process. We went the other direction. We started at the beginning and worked our way to the end of the number. Here we start at the end. We're going to start with that 38. 38 divided by 60, convert it into minutes. Now I'm going to add that to the 18 minutes I already have to give myself 18.6333. So this is mostly happening in the calculator. I add 18 to that to get 18.63333. That's minutes. I still want to add it. I still have the 42 degrees. I need to add that to the degrees. I'm going to take that 18.63333. I'm going to divide by 60 to turn that minutes into degrees. 0.310555555. That's degrees, and I'm going to combine that with my 42. And there it is, 42.310. .55555. When we go from degrees, minutes, seconds to decimal degrees, standard is to go 4 decimal places. I think that process is a little bit easier, partly because it all stays in the calculator. You don't have to, crack pieces off or whatever. Let's try another example. Let's convert 14 degrees, 51 minutes, 18 seconds to decimal degrees. I'm just going to start this off in my calculator and keep it right there. What's my first step?
18.
Perfect. We start at the end and work our way backwards. 18 divided by 60 to give us 0.3. Then what? Add that, because that's now minutes. Add that to the 51 minutes. 51.3 minutes. Then what? Divide that by 60. Make it degrees. We got 0.855 degrees. And then add the 14 to it. 14.855 degrees. Now it's only 3 decimal places, but it came up perfect, so that's fine. It'll just go 3 decimal places. What do you think? Having fun yet? Right now, I've got to double check to make sure I got the packet out there on Blackboard for you. I don't think I got week 5 put out there for you yet. I got some of it though. I've got to put a packet out there for you. It'll be, what it will be is it'll be page 266 in the packet. And we didn't get through the operations. We grabbed a hard copy of the packet here. Those of you in the room here, I'll give you a hard copy. So for now, it'll be 1 through 41. I said I will get an electronic copy of that posted on Blackboard right away. Those of you at home, that'll be out there within just a few minutes. For those of you in the room here, if you want to get started working, you have a couple minutes to work. I'll be here for any questions. Otherwise, we'll see you all tomorrow on lunch.